Correct. So that's that. Now, non-response adjustments. So you go out and do your survey and people don't cooperate with you. And you got to, if you just took the base weights for your respondents and suppose 30% of them responded, if you sum the base weights up for the respondents, those are not going to add up to the population size because you don't have enough of them, right? So the idea of non-response adjustments is you just kind of ratchet the respondents up to have bigger weights to account for the ones that didn't respond. The idea is real simple. The way that people have dreamed up to do the adjustments can get sort of complicated, but don't lose sight of the fact that that's all you're doing. You're just increasing the weights of the respondents. Now, you need, or at least we statisticians think you need some theory behind why you're going to do something. So there are different ways that people have thought of to justify this. And the two big ones are deterministic response and stochastic response. Now, deterministic just means that, I got the survey I want to do, I got a population I want to survey, there's a segment of them that are going to respond and a segment that are not going to respond. And that's the way it is for all time. If I were to go out and do it all over again, the same units would not respond. The same units would respond. It's all cast in stone what's going to happen. Now, that may make some sense. Some people are just sort of hardcore non-respondents. They would never participate in your survey or any other survey. But to get anywhere theoretically, the second approach is the one that makes the most sense, at least as far as developing theory that you can apply. So stochastic response just means that there's some random chance that everybody would respond. You hit them when they're in the right mood or the right day, or if the survey is interesting to them, there's some probability that they would participate. And there's a probability that they would not participate. So what you want to do is estimate that probability given the data in hand. And then, given an estimate of the probability, what you do is you take the respondents and then divide by that probability, or the inverse of that probability is a little weight that you use to increase the base weight. It's like you're laying another step of sample selection on things. That's all it amounts to. So in the stochastic approach, our job is just to estimate those probabilities of response. Now, these concepts that people like Don Rubin and Rod Little have come up with for missingness are useful here. And there are three categories that they talk about. One's called missing completely at random. So what that means is that it's just like another step of simple random sampling to get a respondent. Everybody's got the same probability of response. You draw your first sample, and then you draw what amounts to another simple random sample to get the respondents. Well, that seems unrealistic. It's just not complicated enough to describe what typically goes on. The one that is a step up in complexity is called missing at random. And what they mean by that is that there are some covariates that help you predict whether somebody responds or not. So if you can use those covariates and model the probability of response correctly, then you're good. You can make an adjustment for non-response. And that's the situation we like to be in. Now, a requirement to do that is that these covariates or auxiliaries are known for both the respondents and the non-respondents. So that's kind of a limitation because you may not know that much about your non-respondents. It depends on the survey. In a telephone survey, you may decide that some of these numbers are residential household numbers, but you don't really know much about who lives at the number unless you can match it against one of these address lists, and then you may have something. So, on the other hand, in a school sample, like monitoring the future, you can get really detailed information, at least on the schools. So if the schools don't respond, you're not going to know things like the enrollment and the proportion of kids who get free or reduced price lunch, and a lot of other things about the school that you can use. And you know that for the respondents and the non-respondents. So that's a good situation. Now, the worst one is called non-ignorable non-response or not missing at random. And that's one where whether you respond or not depends on the things you're trying to measure. So if you're trying to poll people about who they're going to vote for, and who they're going to vote for, like are you going to vote for Trump in the next election? If your chance of responding depends on who you're going to vote for, then that's trouble because you don't have the information on who they're going to vote for the non-respondents. The respondents will tell you, but you got a situation where you don't know enough to account for that. And that, that's the worst. And that's what you always fear you're into. But you don't really know without some special study where you kind of go down and you convince these non-respondents to a subsample to participate and find out what the real answers were. Another example might be in the health and retirement study or the panel survey of income dynamics. If the rich people won't cooperate with you, and one of the key things you're measuring is income and wealth, then that's non-ignorable non-response, which is, you don't want that. You're in trouble if that's your situation. All right, so here's one way that people think about these things. You could put your sample units, both the non-respondents and respondents, in some cells, and you make a non-response adjustment within the cells. You increase the weights of the respondents to represent the non-respondents. And when is that effective? Well, there's an easy formula that Graham Calton and Maligali came up with, which is it writes the bias of an estimated mean this way. It depends on the covariance of what you're trying to measure, y, I in this case, and the probability of response. So this goes along with what I was just saying. If there is a covariance or correlation between the analysis variables and the probability of responding, you got a bias. It doesn't matter if it's positive or negative. You still got a bias. If there's no correlation between what you're measuring and the probability of responding, then you're okay. So if you can, create some scheme where you put things in cells where there's no correlation, then you fix the problem. So, the question is how do you do that? one way to do it would be to create cells where everybody has got, essentially the same analysis variable value. Or at least you're willing to say, I can model those as everybody has the same mean in a cell. Now that's kind of hard because there are many different analysis variables in your typical survey. So you might be able to do it for one, but you can't do it for all. Plus, you don't know the analysis variables for the non-respondents. You may know things off your frame that are kind of correlated with them. The other thing is, if you can estimate the response propensities, these PIs, you could create cells where everybody's got the same response probability, or at least really close to it. And as a practical matter, that's the one that's most doable. Now, as far as the mean square error goes, Little and one of his students, Vardavarian, showed back in 2005, it's actually most important if you can get the Y's right, the analysis variables. That's better than getting the response propensities right. But as I say, that's hard to do. So oftentimes what happens is whatever covariates you got on both the respondents and the non-respondents are at least somewhat predictive of both response probabilities and the analysis variable values. That's a good situation in the sense that if you equalize the response propensities in a cell, then at least you've gone part of the way toward equalizing the means of the analysis variables. And, that's what you're sort of backed into a corner, and that's how you do it. You use the auxiliary data you got and do the best you can. Now, I guess we should take a break. How about come back at 10:15? 7-minute break. Is that good? Maybe 8. Yeah. Okay. Back on the bus. So let's talk about how to actually do this. This is one way to do it, at least. There's 6 steps here that I've listed. What you do is you fit a model to predict response based on the available covariates. So this is, typically logistic. You code all the sample cases, respondents plus non-respondents. 1 if they're respondent, 0 if they're non-respondent. And fit a logistic regression. You could fit, if you like, another binary regression like Probit or complementary log-log. You can do one of those. The difference is pretty small, typically. Now, you could just use the inverses of those estimated probabilities for the respondents and divide the base weight by that probability, and you've got an adjusted weight. What that is supposed to really mean is it's the probability that a particular unit is included in the sample, that actually shows up in the sample once you account for randomly picking them to start with and they're randomly responding in the next step. But what will tend to happen in some applications, at least, if you've got quite a few covariates that have different ranges, continuous ones, categorical ones, you'll get a pretty big spread in these estimated probabilities. And the thing you kind of watch out for is if you have real small estimated probabilities for some units, the inverse of those will be a big weight adjustment. So that'll tend to make your weights vary a whole lot. Plus you don't, nobody's ever that confident that these non-response models are perfect. So you kind of distrust those extreme adjustments. If, on the other hand, you sort those estimated probabilities, as in step 2 here, and you divide them into cells, and then you use a common adjustment within the cell, that's a little less extreme. It's a way of smoothing out these extreme low response probabilities is what it amounts to. So sort them from low to high in terms of probability of response. And you're doing that for both the respondents and the non-respondents. And then you divide them into cells with about the same number of units, initial sample units in each cell. And why do you do that? It's like, think about it, you're estimating a proportion of people who responded, so that, in a simple case, the variance of that looks like PQ over N. If you want to equalize those variances, and the proportions of response don't vary that much from one cell to another, you want to put the same number of sample units in each cell. So it's not the same number of respondents. It's the same number of initial sample units, respondents plus non-respondents. It's kind of a critical thing that people get confused about. And then you calculate a single non-response adjustment within each cell. So there's a bunch of ways to do it, which I'll show you. And then you multiply the weight, the incoming weight, like the base weight of each respondent, by the non-response adjustment. And that's it. So at the end of that step, only the respondents have got a non-zero weight. Yes.
So for at step 4, when we divide them by cell into this homogeneous strata based on this probability of response, so when we compute non-response adjustment for the cell, do we do a specific model within the cell for the response?
Typically, no.
No.
The question was, do you have a different model in each cell for non-response adjustment? The modeling comes overall in step 1. So you have a single model that you hope fits for everybody. Now, it can be kind of a complicated model. It could have, if you're doing people, it could have age, race, ethnicity, sex, education level, and interactions of those things. Whatever you feel like is a realistic predictor of response. Now, the thing that limits you on how complicated you can make that model is the covariates that you've got for the non-respondents. So, yes.
We have a question from the chat. Can you talk about missing covariates in these propensity models? So maybe we have like an administrative data set or something from a prior wave where there's some item missing.
Yeah. You throw up your hands and quit. Nah, you impute. As long as it's not terrible, the degree of missingness. The usual thing would be to impute those missing values. If you got education level for 80% of your file, it wouldn't bother most people to impute for the other 20%. And there's lots of ways you can do it. Hot-deck imputation is real popular, where you put things in cells that you think are homogeneous in some sense, and then you randomly draw the value from a unit you know about. and give it to a unit that's missing. That way you get to use more covariates.
Okay.
Yeah, that's the thinking.
And then this is a follow-up question. Actually came first, but I'm reading the reverse order. This person would like to hear about doing non-response adjustment in a longitudinal study where you have more data on wave-to-wave longitudinal adjustment.
If in something like the what's an example, current population survey, where you're in 5 times, you may have a respondent at wave 3 who responded in waves 1 and 2. So you actually got some data on them from 1 and 2. You can use that to do a non-response adjustment in wave 3. It's perfectly legitimate.
Just as a simple covariate in the propensity model, right?
That's right. Yeah, just as another covariate. Mm-hmm.
So just related to that, like let's say you do have the CPS and you have multiple waves. Can you, when you're computing and let's say it's a different study and I'm getting a new wave of data on all participants, can I use the weight from the previous wave as sort of a base weight and then apply the non-response adjustment to the previous weight, or you can just say no if it's totally incorrect?
Yeah, what would you do? So you got a longitudinal survey and you've got respondents from wave 3, say, and here you are at wave 4. If you've only gone back to the respondents from wave 3, then those weights, I guess, are sort of starting weights, in a sense, base weights that you could use, and you non-response adjust those. Now, in many longitudinal surveys, they'll go, at a given wave, they'll go back and hit up the non-respondents from previous waves too, hoping to convert some of those. And that confuses it some with this weighting. You'd have to think through what makes sense. Yeah, Paul.
Just a quick follow-up on the missing question. Are there cases where it would be appropriate to also just make it categorical and make the missing as a category instead of imputing all the missing data?
Yeah, so the question is, does it make any sense to create a category for missing and then do non-response adjustment within that? Yeah, I think I've seen that done. I mean, you'd have a missing category where you got both respondents and non-respondents in there, and they're missing, they'd have to be missing on all covariates for it to make sense to put them by themselves. But if that's all you know, I guess that...
It comes up in commercial data where a certain subset of the on there will be missing across all the commercial data points.
Oh, I see. A database that you purchase from some vendor. Yeah, I see. I guess, it's either that, make them a special cell, or impute for a critical covariates in some way. And if you know nothing, it's hard to do that. Yeah, if you know where they live, at least that's something. All right. Yes.
So you said one of the main reasons not to use the predicted probabilities from the first model is extreme weights. Something I've seen people suggest is capping it. If your weight's above, say, like 10 or so, just set it to 10. Is that something you would suggest?
Yeah, you could do that. But the thing I like better is kind of a smoothing operation where this dividing into cells and using a common adjustment within a cell is a sort of a smoother.
Doesn't this assume, though, that there's a nice distribution of probabilities to allow you to do that split? I mean, you could have some pretty wacky probabilities that would either give you all cells either contain only respondents, non-respondents, or you have very, you have several modes in the probabilities.
Yeah.
The cells are just abnormally shaped, and it would actually have the inverse effect of sort of kind of.
Well, That, if you had a situation where you got a cell that had virtually all one or the other, all respondents or all non-respondents, that I think is a symptom of the fact that your modeling is unsuccessful and that you're using a covariate that, it's got a bad distribution on the respondents and non-respondents. There's a thing called balance checking that I'll show you in a minute that would be related to that. So let me give you a better answer on that when we get to the balance checking. Yeah, you don't want that, is sort of the short answer. All right, let me show you an example, and then we'll get to this balance checking business. I'm looking at my page number, so I'm on 18 out of 76 here. The last 2 or 3 slides are references, so it's like only 70 slides or so. Probably going a little slow. That's all right. So this uses that same health interview survey data. It's got 3,911 cases. So I've got a variable that I'm calling the response variable. Depends on whether they reported income. Just for illustration. It turns out about 31% are non-respondents if you use this variable to define response. And here are the covariates I got. We've got age, education, coded in categories. Hispanicity, are you Hispanic, are you non-Hispanic? Do the parents of the sample person live in the family? This is kind of an indicator of whether you're taking care of an elderly person, typically. And race. So there's a function in the PracTools package called P-class, here it is, that will do all those steps. It will fit a model, get the estimated response propensities, divide the sample into classes, and return those class IDs on every respondent and non-respondent. And it's sort of, we found we were doing this thing over and over again, so why not write a function that'll do it all in one fell swoop. So what you do is the first parameter that this function takes is a formula for the model. So formulas in R, we've got on the left side the Y variable. So this RESP is 0, 1 for responding or not. And then this tilde thing that lets R know this is a formula that's coming. And then here's my set of covariates. Age, Hispanic race, parents, and education. And then this as dot factor just makes sure that it codes it as categorical variables. If you don't do that, it depends on how they're in your data set, but there's a chance that it'll treat a variable that's coded 1, 2, 3 as a continuous variable, which is probably not what you want. The last category is probably not 3 times as good as the first category in that coding. They're just indicators. And then this next parameter is what type of regression do you want to fit? Do you want an unweighted regression, or do you want to use the survey weights that are input to this step? So those would be base weights, assuming that's the only weighting step we got so far. So you can say weighted or unweighted. You tell it the data file you want to use, and then this link is, this is the way R talks about what, in a general linear model, what kind of model are you going to fit? So logit means logistic regression. Other keywords are probit and C log for complementary log. It would do any of those for you. And then you say, how many classes do I want to divide into? So I'm dividing into 5. And 5 is, yeah, it's sort of a rule of thumb, but typically 5 or 10 catches all the variability you see in the estimated propensity. But if you got a really big sample, there's no reason that you shouldn't divide it into 20 categories or 30 if your sample can handle it. You know, if you got a sample of 10,000, you can think about a bunch of categories. The more categories you create, the more confident you can be that within a category, it makes sense to model everybody as having a common response propensity. That's the idea. All right, so I'm not going to run it, but it creates this list object. The list object has different things in it, but the P dot class is just that's my name that I assign the output. And you do a table on this, and what these are just the labels on the categories, and these are the endpoints. So I've got response propensities that go from 0.453 up to 0.631. There's 778 cases in that. And then it doesn't come out exactly even, but, close enough. There's some, you can't, because of rounding and, the precision on these, how many duplicate values of propensities are in the file, that kind of thing. You can't, it's hard to divide it evenly in all cases. Now, one thing I should say is the internals in R have changed somehow. So if you try to run some of these examples in our book, you're not going to get exactly the same answer. Because, I'm not quite sure whether it's not picking the same sample exactly. There's a way to tell it where to start, with a random number seed. Even if you tell it the same starting places we got in the book, you're not going to get exactly the same answers out. This doesn't bother me too much, but. Oh, let me jump over. Oh, do that. One thing that is true in all these R packages is they really have set it up nicely. You do an R package and it'll automatically create this PDF help file of stuff. This is our package. And I didn't program this. I just sort of followed their rules for how to structure things, and it generates this PDF help file. And it lists all the functions that are in a package. There's this link to the page number over here that is clickable. And then on the left, you'll get this kind of table of contents of everything. So for example, on the P class function, if I go down here, there it is. You'll get a detailed description of the parameters that go into a function and the allowable values. And how good the description is depends on the author of the package. Some people go to more trouble than others. We were pretty anal about describing things because that's what kind of people we are. But other packages are not great in their descriptions. But another thing that you'll get here is it gives you the output that's under the value section, and what you should get are some examples that you can, you could just highlight the code, copy it into the R console and run it, and it should run. If it doesn't run, it's not following the rules that the R people have set up, and your package will get rejected. So, so you understand what's going on in a function, you can run the example and then look at the each step one by one and see what's happening. So I'd recommend that. Okay, so back on the slides. All right, so we do that. Then you got to make an adjustment within each cell. Yes.
Can I ask a question about the code? What decision would you make about weighted versus unweighted? Why would you use one or the other?
Well, here are the arguments. The argument for unweighted is that if you specify the model correctly, then the weights just get in the way. They'll increase the standard errors of your estimated coefficients in your model. Even though they'll be unbiased estimates approximately in a certain sense, so will the unweighted ones. And the unweighted parameter estimates will be more precise. So that's the argument for no weights. The argument for using the survey weights is if you don't have the model specified right, at least you can say, if I did a census of the whole population and the response played out the same way, I'm estimating the best fitting census model. You know, suppose I fit a model with main effects only, but I really should have an interaction in there to correctly describe things. You can, if you use these survey weights, you can still say, I'm estimating the best main effects only model I'd get if I had the whole population in my hands. So, you know, that's convincing to people who like to think in this design-based way, you know, that repeated sampling is everything. And it's totally unconvincing to people who think in a model-based way. So, you know, Michigan's sort of a model-based kind of a shop, I think, and at least in a lot of parts. And so you'll hear that argument up here that unweighted is better more than you'd hear at, say, the Census Bureau, which likes to think in this repeated sampling setup. So, you know, it's up to you. You know, you kind of pick your poison. What you'll find, especially if you've created a fair number of cells, is you'll get almost the same non-response adjustments, weighted or unweighted. And then you're happy because you haven't had to make this philosophical decision about what the right thing is. All right, so here are 5 different ways of doing the adjustment. You could, within a cell, you could just take the average of the estimated response propensities. So, you know, if they, in one cell, if they string way out, this has the same problem as averages in general. They're kind of affected by outliers. Another one is you take the survey weighted mean of the response propensities. Another choice is you just calculate the unweighted response rate within a cell. Number of respondents divided by number of cases in the cell. So that's obviously not affected by outliers. Another one is you get a survey weighted version of that response rate. And then finally, you can take the median of the response propensities, which is, you know, real robust outliers. And again, you know, the same arguments apply to these 6 choices. You know, it depends on, are you design-based or are you model-based? Which one of the ones you want to try to pick?
You know that Rod argues that you should include the weights in the model, but like not as a weighted model, but as a predictor, like any other design feature, and then use the unweighted response rates.
Yeah, that
That's one for me, is that first paper.
right. The Rubin says that sometimes too. So Raphael's comment was that you could, one thing that people have proposed is putting the weight in it, the survey weight as a covariate, which, the thinking behind that is that the survey weight sort of subsumes some other covariates you may not know about and help you predict response. Now, depending on the sample design, that may or may not be true. In stratified simple random sampling, all the weights would tell you, the incoming weights would be what stratum you're in. So you may as well just put a factor in for the stratum in that case. So once you start thinking about particular cases, I think that argument gets weaker. All right. Now, we got a function in Prac Tools that will do these, all 6 of these choices, which I didn't put the code in the notes, but you specify. Let me go to the help file and get down. It's called in our Edge class. Here it is. So it takes some parameters. You got to have an ID on each case. You've got to have the non-response adjustment class, which is the output from that P-class function for a candidate. You've got to have the variable that defines response. You've got to, what's its PREDS? Those are the estimated response probabilities. So this PREDS equal null means there's no default value for that. So you got to specify it. And then weights come in as null, but that's the vector of survey weights, assuming you want to use one of those weighted adjustment methods. And then type is which of those 5 choices that I listed on the previous slide do you want to use? Do you want to use the unweighted average of the response propensities? That's number 1. Do you want to use the weighted average of the response propensities? That's 2, all the way down to 5 for the median within each class. So, we kind of gave you enough rope to hang yourself. Pick the one that you like the best. All right, so that's.
So,
yes.
Sometimes when we use the either weighted or unweighted average response rates, right? Like you would expect that like the response rate would increase, right, as the classes that goes by. But sometimes you don't get that. Like sometimes like one class that proceeds, like it has a slightly higher response rate than the next. Like what do you do?
Yeah, the weights kind of torque things around, which makes you, it would make me want to not use the weights. Because you won't get that with one of these unweighted choices. You're sorting the response propensities from low to high,
right?
Cutting them into classes. So there's no way that the average response rate in class 2 can be higher than class 1, unweighted.
Yeah.
It can reverse with weights though, because it'll, jigger around the distribution. In fact, I think that may happen in this example somewhere. Yeah, I don't see it right here. I've definitely seen what you're talking about. This is how that example comes out. It's table 13.2 in the book. So there's, here are the boundaries of the classes. Here are the counts of persons in each class. here's the unweighted response propensities, the weighted average, unweighted response rate, weighted response rate, median. So you scan across here, and there's some differences. But, I mean, really, I mean, you wouldn't look at them and say, wow, one of these choices is outrageous. You know, they all come out very similar. And they're, I don't see this switcheroo that Raphael was talking about, but it is definitely possible in one of the weighted choices to have, say, the adjustment in class 4 be, these not be in ascending order. Yeah, which seems, it's just so counterintuitive that you'd want to use another choice, some unweighted choice probably. All right, so again, why do we divide them into classes? It's to kind of smooth out extremes. That's the only reason. Okay, so now let me talk about this balance business. And this is relevant to your earlier question. The idea of this balancing on covariates was developed for application in observational studies where, these things where you don't really have a designed experiment, but you got a treatment and a non-treatment group of people, and you're trying to figure out what's related to some response variable. Like you got a pile full of people, some of whom have smoked for 30 years, some who have not. You've also measured on each one whether they've developed lung cancer, say, and you're trying to see, is smoking related to lung cancer? Even though you didn't design an experiment, you can't randomly assign people to smoke for 30 years and see what happens to them. You've got all this kind of found data, which is how epidemiologists have worked for years. And you want to see, well, is it smoking that seems to be related to having lung cancer? Or if you account for a bunch of other covariates, does the effect of smoking go away? So this balance idea is we're trying to predict response probability based on covariates. So when I divide things into cells, what should be happening is, from one cell to another, I'm going to get ascending probabilities of response. Because I'm predicting that based on the covariates, I ought to have different means of the covariates across the cells, right? Because the covariates predict whether you respond or not. My responses are different from cell to cell, so my covariate means ought to be different from cell to cell. But what you want within a cell is that the response probability is about the same for the respondents and the non-respondents. Because you're trying to create a homogeneous cell. Everybody's got about the same response propensity. Well, if that's true, the means of the covariates within a cell ought to be similar. Not much different. So this Ralph D'Agostino, a long time ago, came up with a simple method of doing it, checking it. You could just look at the average response propensity estimated for the respondents and the non-respondents in each cell. That'd be a good idea. D'Agostino's method was, well, I'm going to predict each of the covariates based on what cell they're in, whether the unit is a response or not, and then the interaction. Now, what do I expect to happen? Like here, if I fit a logistic model, say I got a covariate X, or Yeah. Suppose X is age. That's my covariate. I want to predict that just using an ANOVA model based on the class that you're assigned to, whether you're a respondent or not, and the interaction of class and respondent. Well, if the covariate means are different from class to class, P class should be what? Significant or not?
Not significant.
Significant. Because you want the mean to be different from class to class of the covariates, which in turn implies that the mean or the response propensity is going to be different from class to class. So you want that guy significant. Now, should response 0, 1 have an effect on this covariate? No, because you're trying to create classes where the response propensity in a class is the same for respondents and non-respondents. And if this thing's non-significant, the interaction ought to be non-significant too. And then if you got categorical X's, or dichotomous, just run a logistic model and check the same stuff. So here's how it comes out in my example. I'm running a GLM on predicting age based on these 3 things. And here's my ANOVA table. The way you get a ANOVA table out of R is you save the output of that regression in some object, check 1 in this case, and then you do a summary. And it prints this. So, P class. Lots of stars means very significant. P-value is essentially 0 here, so that's really significant. And that's what you want. We want the mean of age to be different across the classes. And here's the response main effect, which is this RESP is just a 0, 1 variable, so I don't have to say it's a factor. It's treated like 1. That is highly non-significant in p-value 0.987. So that's what I want. And then the interactions are all non-significant. So at least on age, we've succeeded here. So you'd go through and I had a model here where response was predicted based on age, whether you're Hispanic or not, your race, parents at home, education level. You go through all those covariates, run this check model, some ANOVA model or a logic model, and just look at the coefficients. And they all, you're not going to come out as slick as the table I showed you, where it's, totally unambiguous that age is doing a good job. And then, you'll have to decide if you're imbalanced, or if, in this example you pointed out earlier, if you ended up with a cell that's got almost no respondents or non-respondents, a balance check is going to fail. Now, another thing that the good packages will tell you if they run a logistic regression or something, and you got almost everybody in a cell is either a respondent or a non-respondent. You'll get this thing that's called quasi-complete separation. That's the lingo that's used. What it's trying to do, like if you're running a logistic model to predict response, it's trying to predict everybody has a probability of response of 1 or 0 in a cell. And the way it does that is it shoots one of the betas off to plus or minus infinity, and you won't actually get convergence of the model fitting algorithm, and then you'll get this warning message typically. And SAS for sure will give you output without necessarily telling you, giving you a big warning that something may be wrong here. You'll see a great big positive or negative beta, and then a gigantic standard error, which is sort of your tip off that something is messed up. So what should you do? You need to do basic tabulations to start with before you jump into model fitting. You ought to take your cells, do a cross tab, or just a frequency tabulation of cross tab of age by response, non-response. Look at it. Is there a cell with almost nothing in there? That's bad. You got to reform your model some way if that happens. And it's easy to forget to do that. In the fog of war where you're trying to get things done, you're on a schedule, you buzz through your model, you make your adjustments, you get the file delivered to the client, and then the client starts poking around and finds something really funny looking, and you don't want that. You want to catch those things yourself. All right, so here's state of code that'll do the same thing. And I don't know how you feel about Stata, those of you who are regular users of it, but their programming syntax really gives me trouble. Some of you, if you use it all the time, you just get comfortable with it. But I never did. Okay, but that's just personal prejudice. All right. Any more questions on that before we keep going? What else we got coming here? Playbooks. We're up to needing another break probably. You're getting quieter all the time. That's a sign that could be break time. Yeah, let me do a couple more slides. We'll get up to weight calibration, then we'll take another break. So what I showed you with the logistic regression modeling or binary regression is not the only way you can do this. Another good way is use a classification algorithm. Like CART or Random Forest, something like that. There are fancier ones that are out there. And the idea there is that you take response, non-response, you feed the algorithm a bunch of covariates, and then it starts kind of drawing a tree of classification groups that it has found distinguish response rates really well. And you'll definitely get something different than what you'd get out of a logistic model if you do this. Now, one package that does this is called rpart. Anybody ever use that? Yeah, it's it's one of the first. It implements this thing called CART, classification and regression trees. And what it's got some real advantages. It will automatically figure out interactions of covariates that are relevant. what it does is it starts at the top. It looks for the best covariate that's predictive of a response, and it splits the file in two pieces, based on values of that covariate. That's the first branch in the tree. So you split into males and females, and then you go over to the males, and you look for the next best covariate that predicts response. And suppose it's education, and it splits that on something like high school and below and college and above, that kind of thing. And then it goes into one of those branches like high school and below, and it looks for another good split. And it's real satisfying what comes out typically. You feel like it's really worked over the data in a way that I would never have thought of in advance. And we'll find some really interesting cells. The last set of cells down at the bottom of the tree are what you could use for non-response adjustment. And one thing that's true about that last set of cells is they will not have the same number of sample cases in them, just because of the way that the splits occur. It doesn't control that at all. There's a parameter where you can limit the smallest size of a cell. So it's a good idea to use that parameter. Now, down at the very bottom, you essentially have this very complicated model that predicts response. You get a certain combination of age, race, sex, education, whatever else you input, defines one cell, and a different combination defines the next cell. And there's all these crosses that have been found. And the idea is, it quits when it can't split anymore, which just means that the response propensity can't be better predicted for that branch of the tree by more splits. So when it gets to that point, you feel like you've got mark, missing at random. Respondents and non-respondents have got the same probability of response, and you quit. Now, it's been shown that this particular algorithm in our part, in some applications, will pick out, it'll tend to pick out too often categorical variables that have got a lot of categories compared to ones that have got like two, say. And if I remember right, to see this error or this issue, it helps to have some continuous variables in there. So you got a mixture of categorical and continuous. And it's actually biased in the sense of not estimating the response propensities correctly, because it tends to favor these covariates with a lot of categories. Like education level, in my old example, I had a bunch of them. Gender's only got two. So there are solutions to that. There's one called C-Forest. That's an R-part package that is better in the sense that it doesn't have that particular defect. And C-Forest is just, oh man, is it slow. It's painfully slow. But, if you set it loose and you go off and eat lunch or something, it'll be done when you come back at least. And if you sit there and watch it, though, or if you're trying to do a simulation study where you call it over and over again, then you really get irritated. Another one is called GUIDE, which is an acronym for something that a fellow named Wei-Yin Lo at Wisconsin developed. So naturally, he thinks it's the best, but it's not in R. It's a standalone compiled set of code. So you'd have to, use it off to the side and then integrate its output. But it's a possibility. Now, which is better? Propensity cells versus this classification algorithm. In principle, I'd think that classification algorithms will give you a better model. But you got to watch your step that it doesn't create really small cells for you and lead to adjustments that vary a whole lot from one cell to another.